Have you ever been part of a group project where like one person did absolutely all of the actual work?
Oh, yeah, always.
Right. And then another person contributed basically nothing but terrible, confusing advice. But then at the end of the semester, everyone in the group gets an A.
Yep. The classic participation trophy.
Exactly. And you probably remember that that burning sense of injustice, right? That feeling that the system was totally broken because it couldn't actually tell the difference between the person carrying the team and the person just, along for the ride.
It's incredibly frustrating.
It is. Well, so as we try to build more advanced artificial intelligence, we're actually running into that exact same problem.
Yeah, we really are.
We are accidentally building AI systems that act just like that terrible college study group. So Fudan and Peking universities recently released a new research paper, and it introduces this framework called TRACER. It's designed to fix this exact issue. So our mission today for this deep dive is to unpack how it actually works.
Because right now, as large language models are increasingly being asked to work together to solve complex math and science problems, they're really struggling to genuinely collaborate.
Right. And they need to figure that out.
Exactly. The timing of this research is critical, honestly. We're kind of hitting a wall with how we train AI. So by the end of this deep dive, you will understand a completely new mathematical approach to AI teamwork.
Which sounds complicated, but it's super fascinating.
It really is. It's an approach that teaches AI agents when to speak up, when to stay perfectly quiet, and how to operate without anyone free riding. It's a fundamental shift from how we currently build multi-agent systems.
And understanding the mechanics behind it requires us to sort of rethink how AI learning actually happens.
Yeah, absolutely.
So let's establish the current landscape first.
Yeah.
We know that single large language models struggle with multi-step reasoning, right? Because they just predict the next token.
Right, exactly.
So chaining multiple models together in a multi-agent system makes logical sense. But you'd think that adding reinforcement learning to that team, giving them rewards for good answers and penalties for bad ones, would create, like, a super team.
You would think so, yeah.
So why is integrating reinforcement learning into a multi-agent system causing such massive failures right now?
Well, it comes down to a fundamental flaw in how the reward signals are distributed. Think of it like a firm of algorithmic stock traders.
Okay.
You have one trader whose job is to pick the stocks, right? And an analyst whose job is to review the risk.
Makes sense.
So the trader makes a brilliant portfolio choice, but the analyst runs their model, gets the math completely wrong, and tells the trader to dump all the stocks.
Oh, no.
Yeah. But the trader ignores the bad advice, holds the portfolio anyway, and the firm makes $1 million.
Okay, so they won in the end. But under standard reinforcement learning, the system only looks at that final $1 million profit, right? So the team succeeded, which means the system sends a positive reward signal back to both algorithms.
You nailed it. The brilliant trader gets a mathematical bonus, and the terrible analyst also gets a bonus.
Wait, so the bad analyst gets a reward just for being in the room?
Yes, and that is the core of the multi-agent dilemma right there.
Yeah.
The researchers explicitly highlight this in the paper. They call it role-level free riding.
Role-level free riding,
Yeah.
wow.
In their specific test scenario, they use a two-agent team. So there's a proposer generating mathematical solutions and a reviewer checking the work.
Just like the trader and the analyst?
Precisely. When the reinforcement learning model only grades the final outcome, a bad reviewer essentially gets a participation trophy. It learns that outputting flawed logic or terrible advice still leads to a positive reward.
As long as the proposer is strong enough to, like, carry the team across the finish line.
Exactly.
Okay, let me push back on that for a second. Don't we already have AI frameworks designed to prevent this through, like, debate?
Well, we do have debate frameworks, yes.
Yeah. Because we see demos all the time, right? Where multiple agents are prompted to argue with each other, critique each other's code, iterate until they find the truth. If they're already capable of cross-examining each other, why do we need an entirely new training architecture?
That's a great question. But those existing systems, they rely on rigid, handcrafted rules written by human programmers. The prompt basically forces a script.
What do you mean by a script?
Like, it explicitly tells them, Agent A, propose an answer. Agent B, critique it. Agent A, revise your answer based on the critique.
Oh, I see.
The agents aren't actually deciding to collaborate. They're merely imitating the structure of a collaborative meeting because the prompt forces them to output text in that exact sequence.
So they are acting out a play about a meeting rather than actually having one.
That's a perfect way to put it, yeah.
Which means if the proposer gets the answer perfectly right on the very first try, that rigid script still forces the reviewer to say something.
Yes. And that leads to a phenomenon the researchers call an oscillating local optimum.
An oscillating local optimum. Okay, break that down for me.
Let's say the math problem is complex, but the proposer nails it immediately. Boom. Correct answer. But the system forces the reviewer to generate a critique anyway.
Because of the script.
Right. So to fulfill the prompt, the reviewer might hallucinate an error that doesn't actually exist.
Oh, wow.
And then the script forces the proposer to revise its answer based on that flawed critique.
So the forced interaction actually degrades the output.
Exactly. The proposer gets confused, abandons the correct answer, and generates a wrong one just to satisfy the rule that it must revise.
That sounds exactly like a terrible corporate brainstorming session where people start changing perfectly good ideas into bad ideas just to justify being in the room.
It really is. And the computational waste is staggering. These systems consume enormous amounts of inference compute just arguing in circles.
And often moving further away from the correct solution.
Right. Simply because they don't know how to stay quiet. And this is the exact failure mode that TRACER was built to solve.
Okay, so if rigid rules and forced debates create these oscillating optimums, how does TRACER actually restructure the system to fix it?
Well, TRACER stands for Turn-Level Regret, matching with Inner Reinforcement Credit for collaborative reasoning.
That is quite the acronym.
It is a mouthful. But the defining feature here is splitting the problem into two distinct architectural layers. Splitting the architecture fundamentally changes the agent's behavior.
Okay, so 2 layers. How does that work?
TRACER divides the multi-agent chaos into an outer layer and an inner layer. The outer layer is called the controller regret layer. Its sole function is a simple binary decision.
Which is?
Should this agent speak during this turn, or should it skip its turn?
Oh, interesting. Just speak or skip.
Right. And then the inner layer is the generation credit layer. Its job is to optimize the actual sequence of tokens the agent generates once it has been given the floor.
So it's basically separating the meta decision from the actual work. This maps perfectly to, like, a highly efficient corporate hierarchy. Well, the controller layer is essentially a project manager. They don't do the complex math themselves. They just monitor the state of the project and decide who gets the microphone.
Exactly.
And the generation layer is the specialist employee who actually executes the complex work once the mic is handed to them. The efficiency gain there is huge, because the specialist doesn't have to perform a bunch of exhausting, compute-heavy analysis just to figure out if their input is even needed.
You've got it exactly. That separation of the meta decision from the generation action is the breakthrough. And to make that communication seamless, the framework uses a shared memory interface called the state vote interface.
State vote interface. So it's kind of like a central whiteboard for the team.
Exactly like a shared whiteboard. In practice, the turn-taking has a specific rhythm to it. In the very first turn, the proposer is required to put an initial answer on the board.
Right, to get things started.
Right. From turn 2 onward, the controllers alternate. The reviewer's controller decides whether to speak or skip. Then the proposer's controller decides, and so on. This shared interface tracks a pending answer and a simple vote tally.
So how does the voting actually work?
The voting mechanism is incredibly streamlined. When the reviewer's controller decides to engage, it looks at the pending answer on the whiteboard. If it validates the math, it issues a positive review, which registers as a +1 on the interface.
Okay, and if it's bad?
If it finds a flaw, it registers a -1. The final output of the entire multi-agent system is simply whatever the latest proposed answer happens to be when the loop concludes.
That makes total sense. So let's zoom in on that outer layer for a second, the controller. The name controller regret layer iterates as a really fascinating concept.
It does.
We are talking about an AI manager learning who should get the mic by calculating its own regret. I really want to unpack this. How does a mathematical model actually experience regret? Is it just like calculating a mathematical my bad?
Well, this brings deep learning face-to-face with classic game theory. The mechanism here is counterfactual regret minimization.
Counterfactual regret minimization.
Yeah. It's a concept famously used to train AI to master complex hidden information games like poker. Counterfactual regret is not an emotion, obviously. It is a mathematical delta.
A mathematical delta, meaning the difference between two things.
Right. It calculates the difference in expected value between the action the agent actually took and the action it could have taken if it had followed an alternative policy.
Okay, so counterfactual meaning the alternative reality. Like, what if I had done the opposite?
Exactly. Looking at the mechanics, the controller evaluates those two discrete actions, speak or skip. Let's walk through the matrix for the proposer.
Okay, let's do it.
Assume there is a pending answer sitting on that shared whiteboard. If the proposer decides to skip, to just remain silent, and that pending answer ultimately turns out to be correct, the system evaluates that decision positively.
So the proposer receives a mathematical +1 for basically leaving a good thing alone.
Yes, the agent learns the value of preserving a correct state.
Makes sense.
Now consider the alternative. What if the proposer decides to speak? It takes the microphone, generates a new sequence of tokens that overwrites the pending answer. If that new answer is correct, the proposer receives a +1. It successfully improved or maintained the state.
Right. But here is the critical penalty, right?
Yeah.
If the proposer decides to speak, and in doing so, it replaces a correct pending answer with a wrong one, it incurs a -1.
Exactly.
Yeah.
Because it actively ruined the team's standing.
Wow. So by accumulating this counterfactual regret over like thousands of training trajectories, the AI is actively building an internal confidence threshold.
You're exactly right. If the AI manager is evaluating a pending answer and its internal probability distribution indicates uncertainty, the math dictates that the safest action to minimize potential regret is just to skip.
That is genius. By learning that confidence level, the system essentially slashes those wasted computing loops we talked about earlier.
It does.
It learns to fiercely protect a high-confidence answer and only spend compute to challenge demonstrably weak ones. It basically masters the incredibly rare skill of knowing when not to talk.
Which is something a lot of humans could learn, honestly.
Yeah, no kidding. So we've solved the inefficiency of forced debate. The agents now know when to speak, but we still have to address the free rider problem we mentioned at the start.
Right, the inner layer.
Yeah.
Yeah.
We need to look at the generation credit layer to understand how TRACER ensures the reviewer doesn't still get a participation trophy when it actually does decide to speak.
So this relies on a highly specific grading mechanism called GSPO. That's Group Sequence Policy Optimization.
Group sequence policy optimization, how is that different from normal reinforcement learning?
Well, normally in reinforcement learning algorithms, like PPO for instance, the system waits for the entire trajectory to finish, the whole multi-turn conversation.
Okay.
And then it applies a blanket reward to the entire sequence of actions. But GSPO fundamentally changes how that reward is calculated and applied.
Yeah, so
To understand the mechanics of GSPO, you have to look at how it segments the output. When an agent's controller decides it should speak, the agent generates a sequence of tokens. A dedicated parser immediately steps in and extracts only the specific output generated by that agent in that specific turn.
Oh, wow.
Yeah. The optimization policy is then applied exclusively to that isolated sequence. The agent is graded purely on its defined role.
Okay, so the independence of the grading is what kills the free rider effect. Let's look at the proposer first. The proposer is categorized as a generator, right?
Correct.
Its isolated sequence is evaluated, and it is rewarded with a +1 or -1 based strictly on whether the mathematical answer it generated is factually correct.
Exactly. But the reviewer is categorized as a discriminator. So the GSPO mechanism evaluates the reviewer's token sequence based entirely on the accuracy of its judgment.
It's just its judgment.
Right. Did it correctly identify a flaw in the math? Or did it correctly validate an accurate equation? The reward for the reviewer is completely decoupled from whether the final answer submitted by the team is actually right or wrong.
That is massive. So if the team ultimately submits the correct answer and wins the scenario, but the isolated sequence from the reviewer contained a flawed critique along the way, the reviewer still suffers a negative policy update.
Exactly. The free ride is totally over.
That is amazing.
And the researchers also implemented a strict penalty for ambiguity.
What do you mean by ambiguity?
Well, if the reviewer outputs a judgment that is invalid, like maybe the token sequence is contradictory or it just fails to take a definitive stance on the math, the reward is a flat 0.
So no reward at all.
It receives no gradient update to reinforce that behavior. It forces the reviewer to be precise and decisive.
I have to point out the massive efficiency gain here, too. Because the parser is extracting and grading these sequences based on single-step decisions from the controllers, you don't have to run out the whole multi-turn dialogue just to assign a grade. Right. You are evaluating the reviewer the moment they finish their sentence without waiting for the proposer to respond to it.
Which means you are conducting localized, real-time performance optimizations
Yeah.
rather than waiting for an end-of-episode audit.
That has to save so much computing power.
It drastically reduces the variance in the training data, and it makes the entire reinforcement learning process significantly more stable and computationally cheaper.
So the architecture makes total logical sense. We have an outer layer using game theory to minimize regret and determine participation,
Yep.
and an inner layer using sequence isolation to enforce strict role-specific accountability. But, as always, theoretical elegance has to translate to actual performance.
It does.
And looking at the data published by the researchers, there is a massive anomaly that completely shatters how we usually think about AI costs and capabilities. Let's talk about the data.
Let's do it. So the benchmark testing was designed to push these models to their absolute limits. They didn't just use standard data sets. They evaluated TRACER on GSM-8K, which covers grade school math. But they quickly scaled up to Math 500, which is a highly challenging data set requiring advanced logical deductions.
And they didn't stop there. They also used GPQA Diamond.
Yes, they did.
For context, for those listening, this is a benchmark written by PhDs. It covers graduate-level physics, chemistry, and biology. These are questions that single large language models notoriously fail.
Because they require deep, multi-tiered reasoning where a single token hallucination just ruins the entire answer.
Yeah, exactly. And to run these benchmarks, what models did they test it on?
They utilized two highly efficient models, Phi-3 Mini 4K Instruct and Quinn 2.57b Instruct.
So relatively small models.
Yes. Using smaller models makes any increase in reasoning capability or any decrease in inference cost highly visible in the data.
And this is where that data anomaly appears, because in the current AI landscape, we assume a direct trade-off between accuracy and compute.
We always have, yeah.
If you want a model to solve a PhD-level physics problem, you have to burn an exorbitant amount of electricity and compute power. Take the baseline testing for a widely used method called self-consistency.
Right, let's look at that.
The data shows it requires 10 separate calls to the large language model per task. It forces the AI to solve the problem 10 different times and then attempts to average out the correct path. The brute force cost of that is immense.
It's totally unsustainable. But TRACER completely circumvents that brute force paradigm. When you look at the comparative data, the radar charts they provided, the competing multi-agent systems and reinforcement learning baselines cluster around two failure points.
Which are?
They either suffer a severe degradation in accuracy or they require massive inference costs, consuming vast amounts of tokens to reach a conclusion.
But TRACER breaks that trade-off entirely. It achieves higher accuracy across all three benchmarks, GSM-8K, Match 500, and GPQA Diamond, but it does so while averaging only about 3 model calls per task.
Going from 10 model calls down to 3, while simultaneously increasing the accuracy of the output, proves the efficacy of the regret mechanism.
It's actually incredible.
By mathematically teaching the agents the value of silence, the system becomes not just more intelligent, but economically viable at scale. It delivers superior reasoning for a fraction of the token expenditure.
So, synthesizing all of this, we started by looking at the chaos of standard multi-agent systems, right? We had models that argued endlessly in oscillating local optimums.
Just burning compute.
Exactly. And free-riding agents that absorbed rewards for terrible advice. We discovered that simply forcing AIs to talk to each other through rigid prompts creates an illusion of collaboration, not the reality of it.
Right, because the reality of collaboration requires structural accountability. By decoupling the decision to participate from the act of generation, TRACER fundamentally optimizes the multi-agent workflow. The outer layer prevents the computational waste of forced interaction.
And the inner layer, utilizing group sequence policy optimization, ensures that every agent is graded solely on the merit of its specific contribution. The system mathematically internalizes its own confidence, calculates the regret of unnecessary interference, and executes a streamlined path to the correct answer.
You know, the implications of calculating the regret of speaking unnecessarily extend far beyond training AI model.
Oh, for sure.
Whether you are engineering distributed software systems or managing human specialists, separating the ideation phase from the evaluation phase, and enforcing strict role-based credit, those are universally powerful principles for efficiency.
It's a profound mirror for how we organize our own workflows. Whether you're prepping for a tech meeting or managing a team, clear credit and knowing when to stay quiet are universally applicable.
Absolutely.
Which leaves a fascinating concept to consider as we look ahead. Right now, Tracer is highly optimized for a two-role dynamic, right? A proposer and a reviewer.
Currently, yes.
But the trajectory of AI points toward a near future where we won't just have two agents collaborating. We will have digital workspaces populated by dozens, perhaps hundreds, of specialized AI agents. You will have legal checkers, code compilers, creative directors, and data analysts all sharing the same digital whiteboard simultaneously.
Managing that scale will require the math of counterfactual regret to evolve from a simple binary matrix into a multidimensional web of social interaction and conditional probabilities. It's going to be wild.
The complexity of assigning credit in a 100-agent system will be staggering. But, if artificial intelligence can use game theory to mathematically perfect the art of knowing exactly when to contribute and exactly when to just stay quiet and let the specialist work, maybe there is hope for the rest of us the next time we get assigned a group project.
I think we'd all appreciate that.
Well, thank you so much for joining us on this deep dive. Until next time, keep exploring.